Miss Jody here with our second video to go along with the quantum nature of light, trying to finish up this chapter, chapter 19. We're going to discuss now that we have looked at the theories, the wave and the particle theory of light, and then the combination of the two and the duality side of light. And now we're just going to look at the different types of lamps, the different types of sources of light, and then so the different types of lamps, and then other sources of light like fluorescence and phosphorescence and lasers and all that. Okay, so just to kind of make it simple, I have just written out a little bit about each one of these particular lights, and then I gave you a diagram which will have this page with some of the lamps on it that I want you to use to help understand the lamps, and then there's another page that goes with it for understanding the world of the lasers and how they work. Okay, so types of lamps. So back in the day, before we had anything, right, we had the sun and the moon, and that was created for our use, and we're so grateful for that source of light. And then there was also the artificial light, which is still pretty natural, but we think of it as artificial in the sense of when the sun would go down, what things did we use for lighting up, right? Fires, candles, oil lamps, gas lamps. Eventually, there was the time of, like in Humphrey Davy with the arc lamps and stuff, kind of go along with these particular bulb worlds, the different types of bulbs or whatever you would call them. And so I could put that there, but when we're looking at the bulbs, so from, I don't know what time, in 1879, the incandescent lamp lamp was perfected, obviously by Thomas Edison. We remember when we studied the story of electricity, and we saw that war between Edison and Tesla and the bulbs and all that stuff. So but most people are familiar with an incandescent lamp. So incandescent means glowing with intense heat. And again, linked to Thomas Edison in 1879. Produces light by heating a thin piece of wire, which we call a filament. And the filament, you heat this thin piece of wire to a very high temperature, somewhere around 2,480 degrees Celsius or 4,500 degrees Fahrenheit. So that's pretty hot, right? Now with the incandescent lamps, many years, they started out using a carbon filament. And over here on this particular page, I don't know if this is helping it at all. I'm trying to make it where it's not so bubbly there. I don't know if that's helping at all. But so on this one, I have the little light bulb here. This is the incandescent version of the light bulb. Started out with using carbon as the wire, the filament, and then it moved on to later on many other, but then tungsten is one of the main ones that's used as the filament there. Now, they started with the glass bulb actually being evacuated and it being a vacuum, so that when the electricity came across the wire, it wouldn't just ignite, and of course in the presence of oxygen and stuff, having that combustion. So what they did is they took the oxygen, the air out, and made a vacuum. Later on in time, they started filling the glass area where the filament was housed with nitrogen and argon. So nitrogen, argon. When the filament burns, obviously, like the word incandescent means glowing with intense heat, it burns, it puts out white light. And after just talking about the spectrum of light and how each particular element has a certain line of light that it makes when it's doing its emission spectrum, or lines of light, I don't want you to get confused, and the book talks about this, that when the energy is flowing through the tungsten wire, we have to remember that the energy it's flowing through a solid. So it's a little different. It's not like the light flowing through the gases that's creating the spectra. So it says in the book this way, this being the filament of tungsten. This occurs because the tungsten filament is a solid rather than a gas. The fact that it creates the white light, all of the light, and not just specific colors like we see with the spectrum. So it's a solid. In a solid, the individual atoms are not independent of one another, but instead are linked closely together. Thus, the electrons of an atom are not influenced exclusively by their home atom. In fact, electrons jump from one atom to another in metals and have no home, so to speak. As a result, a photon of essentially any energy can be emitted in one electron jump or another. The outcome is what we would call a continuous spectrum, containing all the spectrum of light. So when we were looking back and we were talking about the spectrum and we were using a light bulb as the source of light to be split into the colors, that's because it was creating the actual continuous spectrum. But when you do this, when the light goes through the gas, then you have your absorption, or if the gas itself is emitting the light, then you have your emission lines. And so when we have the incandescent bulb, we have that really bright white light, and I don't have anything that can represent that bright light white. So, I got to put something on there. It can't just be black and white and not colorful. That would be terrible. So I'll just put my little highlighter, and I'll put the little tungsten thing on fire there. Well, no, not on fire, but you get what I'm saying. And so with this particular light, the incandescent bulb, sometimes the light's so harsh that they will coat the outside, not the outside, the inside of the glass with silica. And that silica will, and I'll just have to do it in highlighter because I still don't have any color that would represent and so if you ever see like a frosted bulb, that's because it's coated with that silica to kind of calm the light down so it kind of doesn't come out so intense. Now, the problem with incandescent bulbs is they produce more heat than light. So we have to keep that in mind. Now, in the incandescent bulbs, we also have the world of the halogens, which are similar in part of this category. Now, what happens is you still are going to have your same filament, your same tungsten, and all that good happiness there, but your gases are going to be different. And so you're going to have in here the gases of bromine and iodine. So halogens, they are part of, if you look on the periodic table, they are part of the group called the halogens. So what happens is the halogens react chemically with the filaments that they can chemically react with that and vaporize the tungsten. So as it gets really, really warm, it vaporizes the tungsten, and then it will be redeposited back onto the filament. As it cools, it will go back onto the filament. So it makes the filament last longer. So if you ever heard of someone saying, oh, wait, that's a halogen bulb, you can just say, okay, it's the same sort of setup, but it's going to have a halogen in it. They use these in like car lights a lot, like headlights for your car, and they last longer. But again, both of these, they're not super efficient. Now I am going to still put my light coming out. Just can't have it looking not beautiful. It'd be terrible, 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 right? Okay, and then with the incandescent bulb world, I'm going to slide back over here. So I have incandescent lamps, and then I got halogen lamps, and I didn't write much more because it kind of goes with this. Just maybe I should have put like, I'll do that, like bromine and iodine, some of the halogens, okay? And then the next set of categories, fluorescent lamps. Now what fluorescent lamps are, they're electrical discharge lamps. So there's a whole category called electrical discharge lamps. And what they do is they produce light by passing an electric discharge, a spark, through a confined gas, causing the gas to glow. So if you can picture in my little fluorescent, so this would be one end here, and this would be another end. And what they do is in the middle is confine the gas. And then what you do is you, the spark will go from one end to the other end, and through that, it will cause the gas to to glow, and because the spark will slide right through that. Maybe I can kind of make that spark will discharge through that. Now, when it does that, that high spark there through the confined gas, what's produced is UV light, some really strong light. But how that helps us is, even though we can't normally see the UV light, when it's inside the fluorescent bulb is coated. It's coated with what's called a phosphor, which is a material that has the ability for phosphorescence. And we'll talk about that next, but you've probably heard of that before. So it can kind of like slowly emit the light that it can absorb. So it's anything that would be like kind of glow in the darkish world, sort of like that. But with the phosphor coating the inside of the tube bright white, inside of the tube becomes bright white when struck by UV. And so as the discharge is going across, then that UV light is produced that then hits the coating of the lamp and then allows it continues to emit that light in a phosphorescent way. And so the gas is a low pressure mixture of mercury vapor and argon. And so with mercury, all of a sudden I'm thinking, mercury, that is Hg, right? See my little thing with writing symbols so that I can always make it easier and make sure I got the symbols. Well, I'll check that. I don't have a periodic table with me right now, but I'll check that. I think that's mercury. All of a sudden my brain's going, is that mercury? Is that mercury? I think it is. Anyway, low pressure mixture of, let's say, mercury, in case I have that wrong, and argon. So that low pressure mixture of those two, when that spark goes across, it creates a UV light, and then this phosphoresces. All right, so, well, it's called fluorescent though, but you get it. All right, so then with the fluorescent lights, we also have what's called the CFLs, which are the compact fluorescent lamps. So they are this same version with the spark and all, but instead of going from one end to the other, it's going through the tube, the spark is, and going to the other side. But these fit perfectly in the regular types of sockets. So that's kind of nice. Now the problem with both of these is that when you are done with them, they have to be disposed of properly, because the EPA requires that disposal be done a certain way because they contain mercury vapor, which can be a hazard to the environment. So you don't want to just go cracking fluorescent bulbs, right? And when you go to dispose them, you can't just throw them in the trash. And that's an important aspect of the fluorescent world. But these guys are more efficient, 1/4 the amount of energy that we use in the incandescent world. So these are a better choice for our lighting. All right, so when we have the fluorescent lamps and then the compact fluorescent lamps, the CFLs. Then we also have what our BP book talked about, high intensity discharge lamps. And those are like those big street light ones, which I didn't do a diagram of, but you know how it said in our book, the mercury vapor lamps or the sodium vapor, and the mercury vapor lamps being the ones that produce that kind of really bright bluish kind of glow to it, because of having that particular mercury vapor. And then this one, the sodium, kind of makes that really yellow, just so we can remember that with the vapor lamps. So what they do and how they work is there's an arc between tungsten electrodes. So they have the two electrodes of tungsten, and then the arc goes between the two, and it's all fused inside of a translucent quartz. And so those will be like street lights and really high powered like stadium lights and stuff like that, putting off lots of light. All right, then the neon lights, that's electric discharges used to produce different colors of light. You've seen the neon lights before, and those are pretty easy. to note. So instead of having the mercury vapor, it can be replaced with the neon gas. So similar like this, but you would replace that with the neon gas. And you can create different colors, not just with neon gas. You can coat the inside. You can still use neon and coat the inside of the lamp to make a different color, or you can use different gases to make different colors, or even you can mix neon with other gases, like a mixture of these two, neon and mercury, actually make the blue glow. So it just depends on what mixes you want to create the effect of the neon lights. And then last but not least, the world of LEDs. Now, LEDs are light emitting diodes. That's what it stands for, light emitting diode. So the light emitting diode, it's certain combinations of semiconductors that produce light at low temperatures when an electric current flows from one material to the other. So what that means is that in my little LED, I have, this is supposed to be different colors of the LED, but of course printed in black and white, but you know what an LED looks like. So we have on the LED the semiconductors. So these are certain substances that are, like they say, semiconductive. And so what you do is you take a negative type and you mix it with, or you push it up against a positive type. And as the negatives flow to the positive in that junction, you have this building of this light source. And so these are very efficient. They last for decades. And so a lot of our things in technology nowadays use lots of LEDs. And then even the LEDs are starting, the regular light bulbs, either the incandescent or the fluorescents, are getting replaced by LEDs. They cost more, but there's actually LEDs that can go into regular sockets now. They just had to convert the alternating current and all that and make sure that, because this would be like a lower, needing a lower source, and so it had to be converted. And then now those LEDs will last way longer than the incandescent or the fluorescent bulbs, and be way more efficient too. So not very efficient. These are take 1/4 of the energy, so these are a lot more efficient than these guys. But then you got the LEDs that are going to be even more efficient, and so we're moving on up in our knowledge, aren't we, of how all that works. All right, then the next thing is the rest of the chapter talks about other sources of light, and we're just going to skim over this, not want to get too in-depth with this, but just so we kind of get a little feeling for it. So fluorescence, it talks about how something can fluoresce. So fluorescence, phosphorescence, and then laser light. So 3 different extra areas of kind of special side of light. And so fluorescence, the first one, glow bright colors when illuminated by ultraviolet light. Electrons absorb UV photons and then immediately emit visible light photons. So this is like the fluorescent lamp we were talking about. So they will absorb that ultraviolet light that was being made in that spark between the two ends of the tube going through the gas. And so they would absorb that ultraviolet light, and then they would immediately emit that light back. And so it was a little confusing because it said it's coated with a phosphor material, which usually phosphorescence materials kind of hold on to their, instead of emitting it immediately, they emit it like slowly over time. So that's why they get the word, the term glow in the dark, because with a phosphorescence, when the electrons are bumped up to the next level, then they will slowly bump back down. When they bump back down, they spit out their light. They spit out their energy in the form of light. But when it comes to usually a fluorescence, as soon as the light is shut off, it doesn't keep doing it. But a phosphorescence, if you shut the light off and it keeps glowing, then it has that property of phosphorescence, as it slowly like spits its light back out and then eventually gets back to its stable place. But it just does it a little slower. So fluorescence, phosphorescence, and then the laser. When it comes to the laser world, it's kind of a neat concept, the lasers, because it's talking a little bit about the situation we talked about earlier about how the electron can get bumped up to a state where it wouldn't normally want to be, and it will become excited. And so if you look at the little drawings down here, these are the drawings from your book. And the first one is, here's the center, the nucleus, and then this is the first level of energy where the electron should be. But he got bumped up to this level. So as he's bumped up, he's already excited. And so this is the important thing about the laser world. He's going to already be excited, and then more energy is going to come in. And so it's kind of get a double whammy. And when it gets a double whammy, when it's time to when he then goes back down to the state he wants to be, instead of one photon of light, 2 will be emitted, and they will be in step, which we call coherent. So laser light is referred to as stimulated emission. Now, the history behind this is in 1917, Albert Einstein had predicted that if an electron already at a high energy state, so already bumped up, was struck by a photon, another form of another light coming in, okay, so another little packet of light coming in, instead of one photon, then 2 would be ejected if this. So I could even just draw this little energy coming in as a photon. So another packet comes in. Oh, well, that would actually look like an electron. What am I thinking? Because that's an electron. Yeah, well, let's not do that. So anyways, so there's my photon. So my photon's coming in, and this electron is already up there. He's already at high energy. And then he gets bumped with another set of energy, and then 2 things of photons come out, and they eject in what we call in phase. So if you remember, we were talking about waves and all that. In phase means you're going to be having the same characteristics. So same wavelength, same frequency, same direction. So these guys are having the same wavelength, the same frequency, and the same direction. And so it's kind of like a double whammy power of light coming at you. Now, in a regular light bulb, like this incandescent light bulb, you can note that you see all of the things are coming out in all different ways and directions and wavelengths and all that, because this regular light bulb, like we just talked about, would be producing the white light that has all the spectra, so it would be producing a continuous spectra. And so nobody is in phase. They're not like working together, going the same path and the same wavelength and having the same frequency. So we would consider that incoherent. But if you could make a way where you could time this to an already excited atom and force it, then add more energy and force it to go in phase, in step, then you could create this powerful light that we call the laser. So the laser stands for light amplification by stimulated emission. So light amplification, LA, light amplification, stimulated emission of radiation. So the stimulated emission of radiation, so that means radiation flying off of it. So that's kind of cool that it's named for what's really happening. And it's neat that Albert Einstein predicted that. He just wasn't able to be the one who actually figured it all out and saw that. I think if I look back in one of my old books, 1916, American scientist Theodore H. Maiman constructed the first laser. It was a simple device consisting of a 1.5 rod of pure ruby, mirrored at both ends, surrounded by a powerful flash lamp. The whole device was encased in a little metal box. And so I've given you a little diagram, and I'm sending you a video on how the ruby lasers work and some of the other lasers that you can put some information, some notes down here on other lasers, but this one will be the first one, the ruby laser, so that we can see how it creates this, direction and this special in phase side of light. And then, like I said, I'll send you some information of other lasers and how we use our lasers, other videos, and then you can do some notes on that for me there on that page. Okay? All right, so that's it for chapter 19. Finally got through that one. And then we move on to chapter 20. And let me see what chapter 20 is. I think it's like the characteristics of light. Yes, reflection, refraction, dispersion, all that stuff. So that one should be easy. And then 21 is all on lenses and instruments. So that's really easy. Magnification, the microscope, the telescope, all that stuff. So that should be easy stuff. And so we're trucking along here. I hope you guys are doing well. And don't forget, keep all your notes on the half sheets and make sure they have the title on them. And hopefully we can get together soon and get those glued in.